Let's move on to the next candidates. Our sixth candidate is Jacopo Bilotto. Hi, Jacopo.
Hello.
How are you?
All good.
Good? Yes.
Yeah.
That's a good start. Rheology of non-spherical particles with applications to food processing. That's your thesis?
Correct.
Good. Professor Jean-François Molinari was your professor for this supervision. Yeah. And so
yes.
When you are ready, Jacopo, you just wave at Maxime over there. Okay? Enjoy.
Thank you. How many of you have eaten rice in the last week? Well, you're not alone. In Switzerland, on average, we eat around 4 kilograms per year per person, and globally more than 600 million tons are consumed. However, to get that white rice from the fields to your plate, each grain has to be stripped of its brown outer skin. This is done by swirling around hundreds of thousands of grains at high speeds inside milling machines. Now, despite hundreds of years of innovation in the process, there are still two main shortcomings. The global carbon footprint of the process is roughly equivalent to 10% of Switzerland's total emission. Worse, these machines are a bit clumsy. They break a percentage of the grains, resulting in food and energy waste. Even a tiny 1% improvement could have a staggering world impact. So why not just build better machines? Well, because it's a delicate balancing act. If the forces inside the machine are too high, you get perfectly white rice, but it's shattered into 1,000 pieces. If the forces are too low to protect the grains, nothing happens, you are left with brown rice. Finding the efficient sweet spot turned out to be harder than I thought at the beginning of the PhD, and that's why I'm still doing it. I work at the intersection of engineering and physics to try and see what happens inside those machines. Rather than building physically expensive prototypes, I build virtual ones, which allow us to simulate how forces are transmitted from each tiny grain to the next. To turn white, the grains need to rub against one another in the container. This process relies entirely on friction. Now, imagine a crowd of people like us trying to exit this room. If everyone walks calmly, there is flow, but there's no friction. While this is great for evacuation, it's useless for polishing. Inside those machines, we want them to jam and stay partly locked in place to shed their skin. Additionally, the rice grains have a peculiar shape. They are a bit elongated. Imagine that same crowd of people again, but now everyone is carrying a ladder sideways. It's a mess. You bump into each other, you might get stuck in the doorway, and if someone pushes you from the back, the ladder might snap. And this is very similar to the physics of rice inside those machines. If the grains all align perfectly, there is very good flow, but little polishing. If they twist sideways too much, the machine might snap them in half. My aim is to understand how this works and design better geometries that allow us to control the orientation and the forces of the grains during the jam. If my research is successful, a few years down the line, when you eat rice, maybe more of it will have made it from the fields to your plate, and possibly with a lower carbon footprint on our planet. Thank you.
Thank you. Thank you, Jacopo.